Hello everybody and welcome back to the DCAC channel, where we solve Leetcode and basically programming questions to kind of prepare for technical interviews. So I actually did some recording for this problem, but it kind of went over my head. So I had to kind of take, I don't know, 10 minutes of break and kind of think about it, and I think I did it way too complicated. Let's try and do this again, and this time have it a bit more simple for everybody's sake, I guess. The problem is 1260 shift to the grid. So we basically have a matrix of size m times n and an integer k, and we basically need to perform a shifting operation k times. We will just ignore the k for now and just implement it at the very end. What I'm concerned right now is just implementing a shift operation, a single shift operation, and a shift operation basically is valid for what it basically does is moves each of those elements one element to the right. So the 1 comes here, the 2 comes here, the 3 comes here, the 4 comes here, and so forth, and of course the very last element comes here. And the way they introduce the basically the validity or the operation is valid. It is just something that is just, I don't know, it's a technical thing that you could follow, and I tried following, and it oh, you can see my output here. Nothing cool. What I'm thinking about is just an easier approach. So, well, what do we have actually? We have a counter, or basically two indices that will go over each cell. For each cell, say for example we are here, we need to move the 1 here, but we also want to save the 2, right? And after we've saved the 2 on the side and then move the 1, we want to basically save the 3 in a second temporary queue and move what was last saved, basically the 2, in its place. And then for the 4 we have the 3, we want the 4 to be saved on the side, and the 3 that was left from before to be put in its place. And it's basically just going over this I don't know if I wanna, if I have to use paint for that, but it's basically we have our elements, right? And for each element we're basically popping the element, and we have this direction. We pop the element, we swap it from what was before here. Let's imagine here there were some more elements, so we are not at the very beginning. We put the last one, we take the new one out, we put the last one in, and for the next one we actually want to also move the new one on this position. So it's basically this circular motion all the way to the very end, and at the very end we just need to put our last element at the very, I don't know, like the very beginning. And this is all we need to do. So you can do this in this complicated fashion, using a lot of indices and kind of like having to think about different levels. What I'm going to do is just have temp out and a temp in, and it's basically exactly what we talked about here. And for the very first one, it's going to be a temp out, which will be grid, and I actually see where I did wrong last time, and I'm kind of doing it this time again. I will assign them very much at the very beginning, so we don't reset them here every time. And now that we have our temp in and temp out, and by temp out is, I mean by this one, because our temp out is basically the temporary variable that on the next iteration goes out from the temporaries. The temp in is the one that saves the new ones. We can also call it temp new and temp old. I don't think it will be better. So what do we do now? For each of those elements, we go over to the next one, which is the one to the right. It's basically this one. And well, assuming we are not at the very end. And actually we're not going to be doing this. We're actually going to be doing this for the very current one. And for the very current one, first things first, we are taking okay, well, I think the new old convention is actually good. Temp new would be our current cell. Basically, when we're at a current cell, we basically first put this into our temp new, and before even doing that, we are actually first going to be swapping the one that was here before that. So temp old would be what was in the temp new, and the temp new would be getting the new one. And here for the cell itself, so we basically firstly we did this operation, then we did this operation, and now we have basically a free spot here to put the very last one, the old, which would be, for example, in this case, this would be the old, this would be the new. We put the old in this place, right? So at this index we put the old one, and we are more or less done. What do we have here? I just want to quickly see if we didn't get anything wrong. The old, the new. The new is basically the element itself, and we don't need to initialize anything like this. And we can actually do this just as is and just see what's happening. What I'm assuming is we basically swap all those elements and we lose the last one, because right now we haven't assigned the very last one. And as we can see, we actually did exactly that. So what do we do now? Well, if we know that our index E is at the very end of our rows, which would be this, and our J is at the very end of our columns, which would be like this. So just quickly to kind of see why these are the rows and these are the columns, we know that our grid is a list of lists, right? A list of lists will represent a matrix. If you start working with NumPy, this will also be your common notation of matrices or vectors or whatever you want to call them. And each of those inner lists represents a single row. So getting the size of this one, like the outer list, gives us the amount of rows, right? And this is what we get here. Getting the size of any of those inner rows would give us the amount of columns. And this is what we get here, basically getting the first row's size or length. And then of course we need to subtract minus 1, because for indexing purposes we are working with -1, so we know we are basically here. And if that's the case, what we are doing is grid 0 0. Well, we can do this just for kind of understanding purposes, or kind of like just to keep the same convention. The temp old would be the temp new, so we basically swap the very last element that we had here in the queue, and we just don't put anything new in its place, and we go straight ahead in putting it putting the same element into the very first element, and we also want to break at this point, because we're not going to be updating anything more. And in this case, we should be getting our shift operation fully working. It didn't work out. Let me quickly see why. I guess I was wrong. Let's see. We got to here. We didn't push this one, which is weird. Let's quickly see the length of this one, -1. I just want to print. I'm not sure why we didn't get. Oops, sorry, whoops. That was weird. No, no airplane mode, please. Okay, let's run it and see what our debugging code here says. So we got 2, 2. Oh yeah, 0, 1, 2, 0, 1, 2. 2, 2 would be here. So at this point we are definitely okay. What I'm thinking about, we did something wrong with our, well, we didn't really do something wrong, we just didn't think about the very last step. And the very last step would be, we are at this place and we actually need to take the 9 out first. So what we do is temp new, so we actually do the same thing. We only, I see. So in this case, we actually do the same old operation, and at the very end, we just kind of see, okay, do we really also have the last element? If so, and the temporary out would definitely not be what we're looking for. We can actually shift them, but I don't think it matters anymore. So we were basically at the very last element, and I kind of skipped the shifting operation for it. So now we will actually do the shifting operation for the last element as well, but we will also notice is the last element. So we will make sure to put whatever was in that element beforehand, which was the 9, into the very first index. And now I'm assuming our shifting operation is done. And it is done. So now we have our grid, and for, I don't know, it doesn't really matter. We just do this many times, and our grid would be a shift operation on the current grid. So the shift operation on the current grid would shift the grid one time each of those times and update it here, and then we can do it again. Can we do it in the return? I'm not sure. Yes, like this. So for one shift operation, it should be basically one shift. For 2 shift operations, we should be getting the 1 at the very end here, and we got it. The 2, the 3, the 4, 5, 6, 7, 8, and 9, and very much basically at the very beginning. So this should be our algorithm, and I don't see. Oh, we have constraints. Okay, note to myself, I really should be looking at the constraints at the very beginning, right? So as we can see, M and N defined as I mentioned. M and N also are not, the dimensions are not greater than 50, which is still quadratic complexity, or M times N complexity, the very least. Why? Because we are looping twice, Like we are basically looping over the whole space of this. Well, actually, it's not. I'm sorry. It's not quadratic complexity. It's actually, well, you can say it is linear with the size of the matrix itself, and of course we are looping this k times, so our complexity would be k times whatever the size of the matrix is. And we know that the values are all integers and that k is maximum 100 times. So we don't see any constraints or anything that our implementation doesn't do any at the beginning anyway. So yeah, our code is slow. I don't know what could be done faster. I guess we could have shifted it mathematically the way they wanted, but I thought this was a more fun approach. It's basically just kind of having an outer bubble that always rotates with the elements. So yeah, I hope it was educational. I hope you also try and do the other approach, because I think this one would be way faster when it comes to computational speed. But even just trying to work with looping through matrices and do stuff with matrix data structures, I think it's pretty fun. So yeah, that was today's episode. I hope you liked it, and see you next time.